Hello, welcome to the beginning of section 7.1, which talks about the integral as net change. So we'll start with our first example. The first example reads, the velocity of a particle is moving along a number line and is given the following function, 2t minus 2, so obviously we have a linear function for our velocity. Time is between 0 and 4. We want to know the position of the particle at t equals 4 if we know that the initial position, s of 0, equals 5. There are two ways to do this. The old familiar way, which will involve solving a differential equation, and of course a new way, which I'll show in a few minutes. And the new way will utilize the fundamental theorem of calculus. Let's start with the old way. So we do know that velocity equals the derivative of displacement with respect to time, so ds over dt, or derivative of position as respect to time. And of course that equals 2t minus 2. So ds over dt equals 2t minus 2. ds equals 2t minus 2 times dt. Now I can take the antiderivative, and we should get s equals 2t squared over 2 minus 2t, don't forget about the plus c. So basically, if you think about it, our position function with respect to time, or our position function as a function of time, will be 2t squared minus 2t squared over 2 minus 2t plus c. The 2's cancel. So we get t squared minus 2t plus c. In order to figure out the constant of integration, we know to use the initial condition. And of course, if I substitute 0 for x and 5 for s of t, or s of 0, I should get the following. So it looks like c is just going to equal 5. So my function is simply going to be t squared minus 2t plus 5. But of course we want to find the time at t equals 4. So if I plug in 4, I work it out, and I get my answer. So this is should be a fairly intuitive way, given that we just had a test on Chapter 6 that dealt with solving differential equations. So the answer is 13. However, we may run into a situation in which it may be difficult to take the antiderivative of whatever function we're given for the velocity. So we want to recall the fundamental theorem of calculus, part 2, that states the following: that if you take the integral of little f of t from a to b, it's going to equal the value of the antiderivative at b minus the value of the antiderivative at a. So capital F of b minus capital F of a. So we can kind of use the same technique for this problem here. Now if you think about it, we were integrating from 0 to 4, and our function is 2t minus 2, which I'll write in a short while. But think about what this means. Using the fundamental theorem of calculus part 2, the integral from 0 to 4 of v of t times dt is basically going to equal s of 4 minus s of 0, because remember s of t is representing the antiderivative of our velocity function. So integrate from 0 to 4 of 2t minus 2 times dt. And here's the thing. We know this. We want that. So we know s of 0 is 5. And we can integrate the right side. That should be pretty easy to do. 2t squared over 2, we just did it earlier, minus 2t. Plug in 0 and 4, those 2's cancel. So working out the right side, we should just get 8. So s of 4 minus 5 equals 8, and you still get the same answer, s of 4 equals 13. So the advantage of this method is the following. When the antiderivative is difficult or impossible to find, analytically, just use numerical integration with the fundamental theorem of calculus part 2. So let's look at example 2. So we're given a velocity function that's kind of weird, negative 2 times e raised to the cosine, and actually let's make that a t there, not an x, cosine t power. So same thing, s of 8 minus s of 0 is equal to integral from 0 to 8 of negative 2e cosine t times dt. If I work it all out, here's what I'm going to get. S of 8 we know is 3.2. S of 0 we don't know. And on the right side, there's no way we could find it analytically. But if you use your calculator, use NINT in the calculator, you should get negative 22.390. When you solve for s of 0, just kind of moving things around, you should get 25.590. And that would be your initial position for example 2. So hopefully you can see the power of this method, that you could do it the first way, just by separating ds and dt, and then taking the antiderivative of both sides, or utilizing fundamental theorem of calculus, you can figure out what the position is going to be at a particular time. So the second way is a little bit more powerful. Let's look at another example. So we can summarize defining example 1 again as a displacement on time interval, as we just saw right there. Now let's start example 3. So here we want to find the total distance traveled. Now remember, when you're working this out, that actually gives you the net area, or in this case, displacement, when we're dealing with linear motion. What we need to do instead is find where the direction changes, or when v of t equals 0. Now if you think about it, our velocity graph, it's linear. It's going to look like this. If you plot some points, pretty easy to do. You got that? And remember what the definite integral does. It finds the area between the curve and the x-axis. So if I shade this, we'll have something kind of like this here. Now note that we have positive area and negative area. So the definite integral from 0 to 4 is no good for us. That will get us the net area, not quite the total distance. So what we need to do is we could make two separate integrals. We can go from 0 to 1, because again, v of t is going to equal 0 at time t equals 1. So I can integrate from 0 to 1. And because from 0 to 1 there's a negative area, I'm going to put a negative right in front of it, plus integral from 1 to 4, v of t times dt. So if I work all this out, I'm going to have negative integral 0 to 1 of 2t minus 2 times dt plus 1 to 4 v of t times dt. Okay, so we want to integrate let me erase that there. I actually got interrupted. Someone's at the door, so I apologize about that. We also want to integrate from 1 to 4 of 2t minus 2 times dt. So if we work each of this out individually, we should just get the following. T squared minus 2t, and of course it's negative, from 0 to 1, plus t squared minus 2t for 1 to 4. Working all of it out, you should get negative 1 here. And over here you should get, I believe, 8 minus negative 1. So negative 1 plus 9, which will just get us, actually, negative 1. My bad. So that'll be 10. And that makes sense because if you think about it, that's a base of 3, and that's a height of 6. So that area is 9. Height of 2, base of 1. That area is 1. 1 plus 9 should get us 10. If we went from, using a definite integral from 0 to 4 of 2t minus 2, then we would have had 8 as our answer, which we don't want. So the total distance traveled is actually going to be 10. Another thing that you want to take note is that the absolute value of your displacement will equal distance traveled, only the direction doesn't change. So another way we could have done this as well is we could have taken the absolute value from 0 to 1, taking the absolute of all that, and that would have been the distance traveled in that direction. Another thing to keep in mind too is that we can take the absolute value of our velocity, which hopefully you guys know is speed. So if I were to take the absolute value, the graph would look like this. And that still could get you an area 10, which also you can use numerical integration if you plug in your calculator, and you can get that as well. I believe that's all that I plan on discussing for this video. So just to recap, if you want to find the position of a function when given a velocity function at a particular time, you could solve like the way we used to do. Remember, velocity is ds over dt. Separate ds and dt, take the antiderivative, plug your initial condition, get an equation, and then plug in the time in which you're looking for the position. New way, utilizing the fundamental theorem calculus part 2, set up like we have it here. Of course, you'll know one particular value for the position at a certain time. And then after you take the antiderivative, you can solve for s of 4 in this case, or in the case of example 2, you can solve for s of 0. And the beauty about the second way is that we can use numerical integration in case it's too hard to find the integral analytically. And then also, we can find total distance, but just keep in mind that you don't want to integrate from 0 to 4 for this case, because again, the velocity or the position, the particle changed velocity or changed direction at t equals 1. So we do two separate integrals, one for the negative area, one for the positive area. Or you could take the absolute value of velocity function, find the value of the integral numerically, and that would work too. Okay, so hopefully this makes sense, and we can pick up on page 3 when we meet again.